Light, color, and radiant energy. Getting ready. How do we see color? What makes blue light different from red light? Why do people who work with X-rays need to protect themselves? Spotlight on key ideas. In this chapter, you will discover 1. The source of colors. 2. The difference between additive primary colors and subtractive primary colors. Applications of primary additive colors, such as color television. How the human eye perceives color. How to explain the behavior of light using a scientific model. And last, how we use electromagnetic radiation, of which light is only a small part. That should be written as, of which visible light is only a small part. Spotlight on key skills. In this chapter, you will combine filters and lights to produce desired color effects. Use a diffraction grating to analyze color spectra. Design your own controlled experiment. Use scientific notation as a way to write large numbers. Record data in a table. What do members of the Green Movement believe in? What does it mean if you are feeling blue? Have you ever heard a successful enterprise described as being in the red? Colors are so important to how people perceive the world that they are used to describe much more than how things look. Colors are often associated with moods, emotions, events, symbols, and attitudes. What exactly is color? Why do some objects appear red while others appear blue? What do you think is causing the bands of color in the photograph shown here? By studying this chapter, you will deepen your understanding of color and the link between color and visible light. You will then discover how light relates to a range of invisible radiation, from radio waves to gamma rays. The chapter concludes by examining some of the many applications of invisible radiation. The sources of color. At one time, people believed that color was something added to light. When white light struck a green leaf and green light was reflected, people believed the leaf was adding green to the light. However, the starting point activity suggests that a leaf will only appear green if there is green light already in the sunlight before it strikes the leaf. Where, though, is the color in sunlight? Figure 9.1. The gorgeous colors of a fall day ablaze through forests, because the colors are already contained in the light striking the leaves. In the 17th century, English scientist Sir Isaac Newton conducted a famous experiment. He placed a prism so that a thin beam of white light could pass through it. When white light traveled through the prism, Newton saw bands of color emerge. He observed that each band of color was refracted at a different angle, producing a rainbow effect. See figure 9.2a. Newton realized that the different colors must have been present already in the white light, since the prism was not the source of colors. Next, Newton passed these colors through a reverse prism. This time, only white light emerged, as shown in figure 9.2b. In this way, Newton showed that color was a property of visible light. He proposed that white light, such as sunlight, is the result of mixing together all the different colors of light. There are two figures here. Figure 9.2a. Newton observed that a prism refracted light into different colors. Figure 9.2b. When passed through a second prism, the refracted light combined to form white light once again. The spectrum. Roy G. Biv, red, orange, yellow, green, blue, indigo, violet. When white light is refracted into different colors, the resulting pattern is called a spectrum. For sunlight, the colors range from red through orange, yellow, green, blue, indigo, and violet. This pattern is called the solar spectrum. You can remember the order of the 7 colors in the solar spectrum by means of a memory aid. The name Roy G. Biv. The R stands for red, O for orange, and so on. Make up a memory aid of your own to help you remember the order of the colors in the spectrum. A rainbow is an example of a color spectrum. See figure 9.3. Figure 9.3. This rainbow was photographed in southeastern Ontario. Notice the pattern of colors ranging from red on the top to violet on the bottom. When light strikes an object, the light may be reflected off the object, absorbed by the object, or transmitted through the object. When white light passes through a blue bottle, the glass absorbs all the colors of light except the blue. See figure 9.4. Figure 9.4, all of the colors of light except blue are absorbed by a blue bottle. Only the blue light is reflected or transmitted. Only the blue light is reflected or transmitted. This explains why the bottle appears blue. Seeing red. The color you see when light strikes an opaque object depends on which colors are reflected and which ones are absorbed. The paper on this page reflects all colors, so you see it as white. The print on the page absorbs all the colors, so you see it as black. Any colors you see in colored photographs depend on the color of light reflected from the photographs. Examine figure 9.5. A tomato under white light looks red because it is reflecting only red to your eyes, as shown in photograph A. What happens to all the other colors if only red light is reflected? The other colors have been absorbed by the skin of the tomato. In photograph B, you see the tomato under red light. The tomato still appears red since red light is not absorbed by the tomato. However, in photograph C, the tomato is illuminated by blue light. Because blue light is almost completely absorbed by the tomato, very little blue light can reflect back. Thus, the tomato looks black with just a hint of blue. Did you know many animals other than humans, for example, cows, deer, and dogs, cannot see colors? They see the world in only black and white. Additive primary colors. The 3 colors, red, green, and blue, are called the additive primary colors. They are called additive colors because Adding all three colors in the proper amounts will make white light, as shown in figure 9.6. The light of two additive primary colors will produce a secondary color. The three secondary colors are yellow, cyan, and magenta. Did you know an electron is a negatively charged particle orbiting the nucleus of an atom? You will learn more about atoms and electrons in your grade 9 studies. Figure 9.6, combining the additive primary colors red, green, and blue produces white light. Television screens use additive primary colors. The screen contains many groups of 3 tiny phosphor dots. See figure 9.7. Each dot glows with a different color when it receives energy from the electrons inside the picture tube of the television set. In each group, one dot glows red, a second glows green, and a third glows blue. If all 3 dots glow brightly, you see white light. The phosphor dots on a television screen are too tiny to be seen from a distance. Thus, you see sections of color rather than individual dots. A section on the screen will look yellow if the red and green dots in the section glow. If the red and blue dots glow, you will see magenta. What combination of glowing dots produces cyan? All other colors can be created by varying the intensities of the 3 primary colors. So cyan would be, if you look at the drawing, cyan would be green and blue. Cyan would be green and blue. For instance, why is the ocean blue? Why is shallow ocean water blue that has white sand underneath? Because the light goes into the water, hits the sand, and comes back out. The reason it's cyan is because the water absorbs all of the red light and doesn't release it. So the light is actually reflecting against the sand and coming back out. And the red is being scrubbed out, so it's a brilliant cyan. It's not because it's reflecting the sky, it's because the water is filtering out the red, and all that's left is green and blue, which is cyan. How we see color. The retina of the human eye contains 2 types of cells that respond to light. See figure 9.8. Figure 9.8. Rods and cones, named for their shapes, are the 2 types of light-detecting nerve cells in the retina of your eyes. Fascinating. Amazing. Looks like some aliens standing on top of each other. Some cells look like tiny cylinders and are called rods. They detect the presence of light. The other cells are called cones, again because of their shape. The cones detect color. There are 3 types of cones, each of which respond to a different color. As you saw in the spectrum produced by a prism, white light contains red, orange, yellow, green, blue, indigo, and violet light. However, cones in the human eye respond mainly to red, green, and blue light. This is why the eye can be tricked into thinking that a beam of light is white when it contains only those 3 colors. This is also why all other colors are seen by the eye in terms of the relative amounts of red, green, and blue light sensed by the cones. Signals from all 3 types of cone cells and rod cells travel along the optic nerve to the brain. The brain then interprets the shape and color of the object that you see. Off the wall. Almost no mammals except primates, a category that includes apes, monkeys, and humans, possess color vision. In those mammals that do have color vision, it is very basic. However, many other animals possess an excellent sense of color. It is highly developed in birds and fish, and insects such as bees see a broader spectrum and probably a greater variety of colors than humans can. To a bee, vegetation we see as basic green would be transformed into a range of hues. Birds have the best developed color sense of any class of animal. They see an enormous variety of colors compared to humans. Some people's eyes have defective cone cells. Because of this defect, they have difficulty detecting some colors. This condition is called color blindness. A simple test for color blindness is shown in figure 9.9. Figure 9.9. People who cannot detect the difference between green and yellow cannot see the 5 in picture A. Those who cannot detect the difference between red and green see the 8 as a 3 in picture B. People with total color blindness cannot read either. I see the 5 and I see the 8. The 5 is not terribly clear, but fair enough. Subtractive primary colors. Now, take a closer look at the secondary colors, cyan, magenta, and yellow. These colors are called subtractive primary colors because some portion of the white light has been removed in order to produce each color. Because cyan is missing only red light. If you shine cyan light and blue light onto the same screen, you should see white light reflected. For this reason, cyan and red are called complementary colors. They are complementary because together they form white light. See figure 9.10. Figure 9.10. What will you see if you shine cyan, magenta, and yellow onto the same spot on a screen? You would end up with a combination of red, green, and blue. Your eye would see the result as white light. Using color filters. Color filters subtract colors from the light they transmit. Remember the blue bottle and why it appears blue? Suppose you combine two filters of secondary colors. For example, place a magenta filter on the stage of an overhead projector. Next, place a cyan filter so that it partially overlaps the magenta filter and turn on the projector. What color do you see where they overlap? Assume that white light consists of red, green, and blue. The magenta will subtract the green from the light. The cyan will subtract the red. This leaves only the blue to shine through, as shown in figure 9.11, combining magenta and cyan filters. Now suppose you used one secondary color and one primary color. For example, place a red filter on top of the yellow filter. What do you see? If you follow the steps in figure 9.12, you will observe that only red can emerge from this combination. You will experiment with other combinations and filters in the next investigation. Figure 9.12, combining yellow and red filters. Applications of color filters. Color filters have many uses. Each time you make a color photograph, for example, you are using filters. Photographic film is made of layers of material that are sensitive to light. The top layer responds to blue light. Beneath this layer is a yellow filter that blocks any blue light from reaching the lower levels of the film. The bottom layers of the film are exposed by the green and red portions of light from the scene. This same principle is applied when skiers wear amber-colored sunglasses while skiing. The yellow in the glasses prevents the blue in the bright sunlight from reflecting off the snow and striking the eyes. This prevents a condition called snow blindness, temporary blindness caused by the glare of light reflected by large expanses of snow. 9.2, a new way of thinking about light. You have seen many situations in which light travels in straight lines. For example, light that shines through a rectangular window will produce a sharp, bright rectangle of light inside the room. Sir Isaac Newton tried to explain why this happens. He proposed that light beams are made of streams of extremely tiny, fast-moving particles. These tiny particles of light, he suggested, could only travel in straight lines. Newton believed that the particles could not travel around objects. Explore Newton's ideas further in the activity below. Looking at waves. Based on what you observe in the previous find out activity, light does not seem to consist of speedy little particles that travel in straight lines. When light passes through a small opening, it spreads out around each side of the opening. To explain this behavior, Dutch scientist Christian Huygens proposed that light travels as a wave, not as a stream of particles. Einstein said it did both, and he actually won the Nobel Prize for saying that light was a particle, and that was his proposal of the photoelectric effect. So I'm not sure what they mean by that in this book. It's a little weird. Examine figure 9.13. The high parts of the wave are called crests. The low parts between the crests are called troughs. As the wave moves to the right, the duck rises up as the crest passes. Then the duck drops down as the trough passes. There's A, B, C, and it says 9.13 water waves. So study that diagram. It's very similar to what we did in chapters 10 and 11, which we've actually already done. The duck and the water around it do not move forward. They just move up and down as the wave passes. It's actually the energy is passing, not the water. The energy is passing through the water. The water stays pretty much stationary. A little circular motion, but it doesn't really travel much. It's mainly the energy traveling through the water. The duck and the water around it do not move forward. They just move up and down as the wave passes. The distance from crest to crest or from trough to trough is called the wavelength. Alternatively, you can think of a wavelength as the distance covered by one complete crest plus one complete trough. See figure 9.14. Figure 9.14, a wavelength can be measured in 3 different ways: the distance from crest to crest, the distance from trough to trough, or the distance covered by one complete crest plus one complete trough. If the wind starts to blow, the water will become rougher. Soon, higher crests and deeper troughs will form. The height of the crest or the depth of the trough from the rest position is called the amplitude, as shown in figure 9.15. The amplitude of a wave indicates the height of the crests or the depth of the troughs from the rest position. The amplitude is a good indication of the amount of energy transmitted by the wave. The rate at which the duck and water move up and down is called the frequency, F. Frequency is the number of cycles completed by one vibrating object in a unit of time. Frequency is usually measured in hertz, or cycles per second. If something vibrates 20 times a second, its frequency is 20 hertz. The wave model of light. Scientists have developed a model of light by looking at how light behaves and then trying to explain what they see. As you learned in earlier science studies, a model is a way of representing something in order to try to understand it better and to make predictions. One of the explanations of light behavior is the wave model of light, which pictures light traveling as a wave. This model does not explain everything about how light behaves, but it helps explain a great deal. Thinking about light in terms of waves helps explain otherwise unpredictable behavior, such as why light curves around an opening. Just as for water waves, the distance between the crests or the troughs of a wave of light as it travels through space is called a wavelength. When light passes through a small opening, the waves spread out. How can the wave spread out depends on the wavelength of the wave. Waves with short wavelengths spread out very little. Waves with long wavelengths spread out more. Explore the relationship between frequency and wavelength in the next investigation. Then, discover the relationship between wavelength and color in Conduct and Investigation 9D on page 286. Light waves in action. We can explain sunsets, such as the one in figure 9.16, using a wave model of light. As light waves from the sun travel through Earth's atmosphere, they strike particles of different sizes, including dust and grit. The longer wavelengths of the reds and oranges tend to pass right through and between these particles. The shorter wavelengths, especially blue and violet, strike the particles and are reflected and scattered off them, as shown in figure 9.17. Some wavelengths of light can pass around particles in Earth's atmosphere. Other wavelengths are reflected and scattered by them. At sunset, the sunlight we see passes through about 700 kilometers of Earth's atmosphere. At this time of day, the sunlight passes through many more particles than earlier in the day. This allows plenty of opportunity for many of the blue and violet waves to be reflected away. Red and orange waves remain to color the clouds of the sunset. Some of the waves with shorter wavelength are reflected into space. However, if you look straight overhead at sunset, you will see blue light that has been reflected toward you. Figure 916, a sunset near Souk, British Columbia. As the golden disk of the sun sinks below the horizon, low-lying clouds light up with shades of orange, red, and purple. Where do these colors come from? They come from the sun. Laser light. In 1966, scientist Theodore H. Maiman became the first person to use a process called light amplification by the stimulated emission of radiation, or laser light. Laser light is quite different from the other types of light you have studied. However, an understanding of the wave model of light helped scientists develop laser light and its many applications. As you have already seen, an incandescent light bulb gives off many different colors. In terms of the wave model, this means that many different frequencies and wavelengths are produced, as shown in figure 9.18a. Moreover, the waves are all jumbled. Crests from one wave might overlap a trough from another, making the waves work against each other. Such light is called incoherent. A laser, on the other hand, emits waves with only one frequency or wavelength, as shown in figure 9.18b. Let's look at 9.18a. An incandescent bulb gives off many frequencies of incoherent light. Figure 9.18b, a laser gives off a single wavelength frequency of coherent light. In addition, all the wavelengths line up to work together. Such light is called coherent. Cool tools. Scientists are using laser light to trap and cool tiny particles of matter. Why? Many properties of matter change as temperature near the coldest temperature possible, which is absolute zero, negative 273.15 degrees Celsius. Physicists are trying to bring small samples of matter to the coldest possible temperatures in order to better understand magnetism and the behavior of particles in matter. They can bring matter to extremely low temperatures by using special lasers to decrease the vibrations of the particles that make up the material. Lasers are used for many purposes. They help read barcodes at a supermarket checkout counters. They sense tiny pits on a compact disc to play music. This book is very old. You may have seen police officers using lasers to measure the speed of cars. Doctors use lasers as scalpels when performing surgery on delicate tissue, such as the eye. On a larger scale, infrared heat lasers are used in industry to make precision cuts through metal. Figures 9.19a and b show how lasers are used in fiber optics. 9.19a. Because of its strength and coherence, laser light can be used to carry information over long distances through fiber optic cables. Such cables use the law of reflection to carry light signals. figure 9.19b. An optic fiber is designed to reflect light so that it is piped through the length of the fiber without escaping, except at the end. Beyond light. Earlier in this unit, you learned that the sun is the most abundant source of light on Earth. However, there is far more to sunshine than meets the eye. In addition to the visible energy that we call light, the sun also radiates invisible energy. The light we can see is just a tiny band of much broader spectrum of visible and invisible energy. You have seen how water waves can be used to represent how light moves through space. However, light is a very different kind of wave from those that travel through water. In a water wave, water particles vibrate up and down as the wave passes through the water. That's what we said before. It's really the energy passing through, not the water. So it is a little different. They explain that very well here, and that's just that one sentence. In a light wave, electrical and magnetic fields vibrate. As a result, light is classified as electromagnetic radiation. Visible light energy and all the invisible forms of radiant energy exist on the electromagnetic radiation spectrum, as shown in figure 9.20. The electromagnetic spectrum. And you can see how visible light is a very small portion of it. Different colors of light represent different frequencies and wavelengths of light. Table 9.2 shows the wavelength and frequency of the colors in the visible spectrum. In the rest of this section, you will examine more closely the bands of invisible energy beyond the red and violet ends of the visible light spectrum. Did you know a nanometer, nm, is equal to 0.000000001 meters? Expressed in scientific notation, this is 1.0 times 10 to the 9th meters. Red light has a frequency of 700 nanometers, which is 0.0000007 meters, or 7.0 times 10 to the negative 7 meters. The nanometer is so tiny that about 500,000 of them would fit across the thickness of a sheet of paper. Math Connect. The frequency of red light is given as 4.3 times 10 to the 14th hertz. This method of expressing a large number is called scientific notation. Yes, you all will be responsible for understanding it. The number 10 to the 14th means 10 times 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 10. And you add all the ones, because that's really, you're all 10 to the 1. How would you express the number 5 billion in scientific notation? You would express the number as 5 billion. In scientific notation, it would be 5 times 10 to the 9th. There's 9 zeros. So you see that the decimal point is understood to be on the far right, to the right of that final 0. And then you count over 1, 2, 3, 1, 2, 3, 1, 2, 3, 1. Okay? So it's going to be 9 zeros. Okay? 9 moves to the left. Infrared radiation. If you could take red light, which has a wavelength of about 700 nanometers, and somehow stretch it out to 1,000 nanometers, it would no longer be light. It would be heat radiation or infrared radiation. Your eyes would no longer see it, but your skin would sense it, You could feel infrared radiation when you bring your hand close to the side of a cup of hot chocolate. There are many uses for infrared radiation because infrared is heat radiation. Anything that is warmer than its surroundings emits infrared rays. Based on this understanding, motion sensors and burglar alarms have been developed to detect a change in the infrared levels in an area if a person is present. Some restaurants use infrared heat lamps to keep food warm. Figure 9.21 shows an infrared lamp being used to warm a baby chick. Cool tools. A thermogram of a hand, like the one shown here, can help diagnose circulation problems by detecting infrared radiation. Warmer areas show up as yellow, orange, and red. Cooler areas are green, blue, and black. Would the problem area show up as warmer or cooler than the other parts of the hand? You see the fingers look very cold, don't they? Figure 9.21, infrared lamps called brood lamps or brood lights are used to keep baby chicks warm. Radio waves. Radio waves. If you could stretch the infrared wave out again even farther so that the wavelength becomes a few millimeters long, you would begin to obtain radio waves. Radio waves have a longer wavelength and a lower frequency than visible light. Different types of radio waves have different uses. Microwaves have the shortest wavelength and the highest frequency of all the radio waves. Microwave ovens use a specific wavelength or frequency of microwave that is strongly absorbed by water particles. When the water particles in the food absorb microwaves, they begin to vibrate quickly and become hot. Only foods that contain water particles can be heated using microwaves. Microwave frequencies are also used in telecommunications. See figure 9.22. Figure 9.22, signals sent by satellites can travel vast distances. One satellite can replace many ground-based relay stations. This illustration is not drawn to scale. Microwaves can be transmitted to telecommunication satellites that orbit Earth. The satellites receive microwave signals, amplify them, and retransmit them to a new location. Microwaves are also used in radar. In this case, microwaves are beamed out through the air. The waves that reflect from an object tell the radar operator the location and speed of the object. As figure 9.23 shows, air traffic controllers depend on radar to guide aircraft. Radio waves with longer wavelength than microwaves are used to broadcast radio and television programs. Most radio waves are harmless. In fact, radio waves are streaming through you right now. However, it is not known for certain whether long-term exposure to sources of radio waves could be harmful to people. See figure 9.24. Let's look at 9.23 for a moment. It says, figure 9.24, scientists are studying whether there is any danger from long-term exposure to radio waves, especially those emitted by electronic equipment such as computers, microwave ovens, and televisions. So far, studies have not yielded clear-cut evidence of harm. I just want to say one thing, that Microwaves are in their own category. They're not considered necessarily part of the radio wave spectrum. On every chart that you're going to look at, except in this book it seems, you have radio waves, and then you have microwaves, and then you have infrared. So microwaves are not considered radio waves. I don't know who considered that, but they're generally considered to have and be their own category of electromagnetic radiation. Okay, it says ultraviolet radiation. At the violet end of the electromagnetic radiation spectrum, wavelengths of 200 nanometers are known as ultraviolet radiation. This radiation is extremely energetic. It causes tanning, which is the skin's way of trying to protect itself from the ultraviolet rays. Ultraviolet radiation can damage the cornea, the front surface of the eye. This can lead to a fogging of the cornea, causing a slow loss of vision. As figure 9.25 shows, sunglasses can block ultraviolet radiation, will protect the cornea from damage. In recent years, more and more ultraviolet radiation from the sun has been reaching the surface of the Earth. This is due to a decrease in the Earth's ozone layer. Ozone, a form of oxygen, is located in Earth's atmosphere about 20 to 25 kilometers above the ground. See figure 9.26. 9.26, Earth's ozone layer, not to scale. The ozone layer is vastly improving. Again, let me just look very quickly. This book was written in 1999. The ozone layer is in fine shape. It certainly goes up and down in terms of whether or not it has a hole, but relative to when the book was written, it is in pretty good shape. Not bad. Not bad shape at all. When ultraviolet radiation from the sun reaches the atmosphere, ozone absorbs much of the UV radiation, preventing it from reaching Earth's surface. However, Earth's ozone layer appears to be thinning. Some chemicals used in aerosol spray cans are able to rise through the atmosphere and break down the ozone particles. Freon, a gas one frequently used in refrigerators and air conditioners, can also destroy ozone particles. Fortunately, many spray products such as deodorants and hairsprays are now manufactured without ozone-destroying chemicals. Also, the use of Freon has been banned in many countries. Did you know bumblebees can see ultraviolet radiation, which helps them detect patterns on flowers? And when it's raining out, you very rarely will see a bumblebee. Even if it's very cloudy, oftentimes you won't see them. They can't see. The ultraviolet radiation is very low. It's like nighttime for them. X-rays. At even shorter wavelengths and higher frequency on the radiant energy spectrum are X-rays. These waves are very penetrating and extremely energetic. X-rays pass easily through tissue, such as skin and muscle. However, X-rays are absorbed by bone. See figure 9.27. People who work with X-rays protect themselves from harmful radiation by leaving the room while the equipment is being used. When a dentist takes an X-ray of your teeth, he or she places a shielding pad on your body to protect you, and then leaves the room before operating the X-ray machine. Figure 9.27. X-rays are commonly used to locate a break in a bone, such as this forearm fracture. Gamma rays. Gamma rays are shown in figure 9.20 on page 293, have the shortest frequency and the highest energy of all the radiant waves in the electromagnetic spectrum. Gamma rays result from nuclear reactions and can kill cells. However, sometimes the ability to destroy cells is useful. When doctors discover a cancerous tumor in a patient's body, they may decide to destroy the tumor with gamma rays. This is known as radiation therapy. As you have learned, visible light represents only a small part of the electromagnetic spectrum. We are surrounded by energy waves. However, many of these waves are invisible. They exist in frequencies we cannot see. Nonetheless, these invisible waves serve important roles, from transmitting music to our homes to saving lives in hospitals. Figure 9.28. People who work with gamma rays must use shielding to protect themselves from the radiation. In addition, they wear a badge, like the one shown here, that registers how much exposure they have had to gamma rays. Looking back on page 293, it says, figure 9.20, the electromagnetic spectrum. It shows the position of the gamma rays relative to X-rays, ultraviolet, visible, infrared, and radio waves. So gamma rays are to the far right, and they have the highest frequency, the shortest wavelength, and the greatest amount of energy.